All right, here's our last video. So we want to do an application of how you can use vertex form to write an equation to describe a situation like this. So we've got that Andre practices free throws at the park, and the ball leaves his hands at a height of 7 feet and reaches the vertex of its trajectory, the highest point, 10 feet away and at a height of 11 feet. So let's find an equation for the ball's trajectory. But first, let's draw a picture to make sure we understand what all these numbers mean in space. So it's saying it leaves his hands at a height of 7 feet. And so let's say that's where x equals 0 here. A height of 7 feet would mean right here. So that's where he's holding the ball. And then 10 feet away from that would mean we just go 10 units to the right. So that's going to be when x equals 10, so it should be a point up here. Y should be 11, the height that it gets. So it means that this is what the trajectory looks like. That's the highest point. It's going to be something like that, and then it starts coming back down. Something like that. Okay, so if we want to find a quadratic equation for the ball's trajectory for part A, we're going to use the vertex form, which says if it's written in the form y equals a number A times x minus the x-coordinate of the vertex, xv, and that is squared, and you have that plus the yv. This means that an equation that looks like this will have the vertex xv and yv, and the a sort of determines how it's shaped, how narrow or wide it is. So in this case, our xv, yv should be 10, 11. So it's going to be minus 10 and then plus 11 on the outside there. So the equation would look kind of like this, but the different values of a are going to give you different parabolas that all have the same vertex. So depending on what a is, you might get a parabola that looks like that, or you might get a parabola that looks like that. Those would all be if a is negative, or if a is a positive number, you'll end up with a parabola that opens upwards, something like that. Those are the way it would come out with different values of a. So let's figure out what a is using the other information. Because you notice all of those things I just erased, those all have different y-intercepts here. There's only one parabola that has the right y-intercept and also has that point 10, 11 as the vertex. And the way we're going to find a is we're going to say, well, let's look at this. This is an equation that actually has 3 unknown quantities in it right now. There's x and y, which are the things you want to be variables, and then there's also a. But if you plug in a number for x and a number for y that you want to have work with this equation, then a is going to be the one variable. So that's what we're going to do. We're going to plug in 0 for x and 7 for y. So that will make this equation look like 7 equals a times 0 minus 10, quantity squared, plus 11. And let's see, the negative 10 squared will come out to be 100. So we can just solve this equation for a the normal way. You can subtract 11 from both sides to get negative 4 equals 100 times a, and then divide both sides by 100. And that will give you negative 0.04 equals a. So that means we now have the whole equation. We're just leaving the x and y as variables because we are trying to find a whole two-dimensional equation that has a graph. So that's going to be negative 0.04 times x minus 10 quantity squared plus 11. And of course the good way to check this would be to graph it on your calculator. Like so. We're going to graph y equals negative 0.04 x squared. Sorry, not x squared. That should be something totally different. It's the quantity x minus 10 squared plus 11. Check out the graph. We can change the window. Let's make the x max be, I don't know, 16, and the y max, I don't know, maybe 16. See what happens, and we get a graph like that, and we can trace. Let's plug in x equals 0, and yeah, we get 7, so it has the right y-intercept. And then you can also trace over to the right to make sure that the vertex is in about the right place, which should be the point 10, 11, which looks like that's pretty close to it right there. So for part B, we want to know, is this trajectory going to go through the point where the hoop is, which is going to be 15 feet over here. So I got 10, 12, 14, 15 would be about here, and 10 feet high is here. Oh, that looks good. So we're saying that's the hoop. Let's see, is that a point on the graph? That point 10, 15. Or, no, 15, 10 is what I meant to say. So if you plug in x equals 15 into this, well, fortunately, we already have it graphed on the calculator. So if you just hit trace and then 15, that will give you x equals 15. And yeah, the y coordinate there is 10. So the trajectory does go through the point 15, 10. But does it actually go in is a trickier question. It turns out that measurement is actually where the backboard is, that 15 feet. So the backboard would be right there at x equals 15. And then the hoop would kind of stick out beyond that. So what might happen is it might bounce off the very back of the hoop. I'm sure you've had that happen when you play basketball, and it's very frustrating because it was like a perfect shot, but it just bounced right off that back part of the rim. Or, you know, it might bounce the right way and go in. You can never tell. So it might go in or it might not. It's up to interpretation and how the ball bounces. So I'll leave that up to you. Maybe you can throw a perfect shot that just barely hits the back of the rim and see what happens. So here's a quick reading question for you to do to make sure you understood what I just talked about, and also an exercise which goes pretty much the same way as that last example. Good luck with that, and I'll see you in class.